Hello everyone. In this video, we are going to look at stress transformation in 2D, and we're going to look at the Mohr circle, which is a graphical method to do that. The material, again, is coming from Mechanics of Material by Gray and Brooks. So if you remember earlier, I had a video that if you had a bar under tension or compression axial load, what happens if you rotate the plane with angle theta and calculate the stress on that? We found that there is a shear stress and a normal stress on that, correct? So now we're going to do it in 2D. This time we assume that you have a 2D stress, so you have sigma x, sigma y, and tau xy on a plate with zero angle. And now if we rotate this plate by angle theta counterclockwise measured from the x-axis, you want to know on this basically rotated plane, or on these rotated plane, this one and this one, what are sigma x, sigma y, and tau xy. So assume that sigma x, sigma y, tau xy on the original plane are given. On this new one, we want to know that, and theta is also given. So all we need to do is to look at the free body diagram of the section plane. So here we look at this plane with normal angle theta, the plane that has sigma x1 on it and tau x1 y1. And here so this is this, if I draw that is this plane here, right? It is going something like this, for instance. And then you look at this portion of the section, and you see on these other planes, you have the original stresses, sigma x, sigma y, and tau xy. And now you say that this whole thing has to be in equilibrium. And so you're going to write the summation of the forces in the x1 direction, the new normal, and y1, the new tangent. And if you do so, then you're going to get these equations. So sigma x1 clearly is going to be multiplied by the area of this plane. And if you remember, the area of this plane is basically the depth of it is the same as this original plane, right? The depth of them are the same. But the length of it, this one, if this guy is, let's say, h, this length is h over cosine theta, and 1 over cosine is secant, so it is going to be h secant theta. Okay, and as I said, the depth of them are the same, b, so one is going to be bh, the other one is going to be bh secant theta. So if this guy, we call it a naught, this is going to be a naught secant of theta. That's the area of this slope surface. So when you multiply it by the area, this is going to be the total force in the x1 direction. Now, sigma x is going to be multiplied by a naught, but not all of that force is in the x1 direction, right? If I go back and look at it again, you can see that the force coming from this element, you have to decompose it along this direction, and this angle is theta, so only cosine component of that in the negative direction is going to be there. For the tau xy, a naught, this component is clearly a sine, and it is again in this direction, negative. Then we have sigma y. Sigma y, again, if you break it down into this direction and this direction, you see that in this direction the x is negative, and again it's a sine, okay? And then tau xy on this plane is also, this one is a cosine. And then you might say, what is this a naught tangent theta? Because it seems like the plane that these forces are acting on, the area of it is a naught tangent theta, and that is actually correct. Because if this plane here has area of a naught, then this one here is going to be a naught times tangent of theta, and you see why. Because tangent theta is the one in front of it to the one across to the side of it. So that is what it is. And remember, when we cut it at angle theta, right, as I showed up here, it's not necessarily going to go diagonal like this. So when we cut it with angle theta like this, then this is the kind of element that you will get, either this one or a rotated version of that. So basically you get this if it's less than 45, and here is that rotated 180 to show you. And clearly the area of this face and this one, they are different areas. So if one of them is A naught, then this one is A naught times tangent of theta, and this one is A naught times secant of theta. Okay, so we have to consider that, and you see they are all considered here. So we do all of that, and we write some of the forces in x1 and y1 direction equal to 0. Now, if you look at these two equations, there are only two unknowns in these equations. What are they? One is basically your tau x1 y1. The other one is sigma x1. That's the only unknown you have. And of course, you can solve two equations and two unknowns. And these are the two equations that you will get for normal stress on this angle plane and the shear stress on this angle plane. Now, if you want to get sigma y1, this other one that we didn't have, and we want to get this one, right? Because so far we found these two. Now we want to look after this. All you need to do for this plane, the normal to this plane, this axis, the angle of it for x-axis, this whole angle is 90 degrees plus theta. So all I need is to change theta to 90 plus theta. And if I plug it into these formulas, I should be able to get my sigma y1. So here, right, I change theta to theta plus 90 degrees. Sigma x becomes sigma y, which is this guy. Tau xy is going to stay the same. Okay, it's not going to change. And you can try that. You can change it to 90 plus, and you're going to see that it's not going to change. It's just going to be negative of this. But these are the three components of stress on this plane at angle. Done. Okay, so we found them. Now, there is another way that we're going to see. This method is called the Mohr circle, which is created by a German person, Mohr. And his story is quite a bit interesting, but I don't want to get into story of that here, how he came up with this circle. But this is a graphical way, and we're going to show you, but we don't really need that graphical way. All we need is these transformation equations. But that graphical way is also interesting, so you don't need to memorize all of these formulas. Now, one thing interesting is if I add sigma x1 to sigma y1, what would you get? Well, if you look, these two terms are the same, except they are negative and positive, so they cancel. Also, these two terms, tau xy's, are the same except positive, negative, so they would also cancel. So you get sigma xy over 2, the average, and this is another average. You add them, you get sigma x plus sigma y, and you get this interesting thing. So this is an interesting thing. It says under stress transformation, under rotation, some of the normal stresses is not going to change. So we say some of the stresses is what we call invariant to the rotation. And this is actually a good check on your numbers here. So basically, if I give you sigma x and sigma y and tau xy and say find the other three, all I really need to find is this first two. So if I find sigma x1 and tau x1 y1, that's all I need. For sigma y1, I'm not going to apply this formula. I just use this one. That's much easier. I say sigma y1 is the original sigma x plus sigma y minus the new sigma x1 that I just calculated. And I get it through this. And this is much easier to do, a simple summation subtraction rather than all these tricks. Okay, so this is really good and it's a good check. Or if you use this formula, you can check it and see whether this equality holds. If it does, you know that you did your calculations right. If this equality does not hold, you know that somewhere in this sines, cosines, positive, negatives, you made a mistake. Okay, so this invariant term is an interesting term. Now, when it comes to design, we always need to know the maximum stress that happens in the body, and that includes all different angles. So when we want to design, we really need to know the maximum normal or maximum shear stress regardless of the angle of the plate, right? So the maximum failure can happen at 90-degree angle or 0-degree angle or any arbitrary theta. We don't care. We just want to know what is the maximum. So for that reason, we have to look into these functions and see for what angle the sigmas and the taus become the maximum. Okay, so we get the maximum one, so we can compare them to the allowable stress terms, and we can see if there is failure or not, or we can come up with safety factors, or if we know safety factors, we can design for geometry or material or both. So we need to know the maximums. For that reason, we are going to take a time derivative from the sigma x1 formula with respect to the angle to see at which angle it's max and set it equal to 0. So if you do that and set it equal to 0, clearly this is a simple trig equation dividing by cosine 2 theta. You get tangent of 2 theta. So tangent of 2 times the angle that makes the maximum stress, normal stress, is 2 tau xy over sigma x minus sigma y. Some books also write it like this. They write it as tau xy, the shear, over the difference between the two divided by 2, like this. They write it this way. And why is it good? Because if you look at these two components, tau xy and the average divided by 2, these are these two coefficients, these two. So it's the coefficient of sine over the coefficient of cosine. That is going to be tangent of, pay attention to this part, 2 times the angle. So if you want the angle, you have to take arctangent from both sides and divide it by a 2 to get theta p. And if you plug that theta p back into the formula for sigma x1, then it is going to give you basically 2 answers. So it is going to be sigma average plus and minus under a square root, again, these two components squared, if you look at them. Okay, so depending on whether sigma x plus y is positive or negative, one of them will be the max, one of them will be the min. So the sigma 1 and 2 are sigma max and sigma min, basically. These are the maximum and the minimum. Remember, when we set it to 0, we're going to get optimum points, max or min. So we're going to get both of them here. One of them is max sigma, one of them is min sigma. These are the angles. And remember, tangent inverse has 2 answers in this case. So you're going to get basically the 2 angles. Okay, and one of them is going to be 90 degrees plus the other one is. Okay, so the angles that you will get is going to be theta p1 and then theta p1 plus 90 degrees. Because the sigma min and sigma max are always on 2 planes that are 90 degrees with respect to each other. About the shear stress, we do similar thing. We take time derivative from the tau xy, x1, y1 with respect to theta, set it to 0. You get tangent of 2 times theta s, the angle that makes shear stress maximum. And again, if you look at this, this is very similar. You can also write it as negative of, again, the coefficient of the numerator is the average, the difference between sigma x and y divided by 2, and the denominator is just tau xy. Okay, and again, if you go back and look at this, right? So you have these components, look at them. You have this one that is negative, you have this one that is positive. Again, it's the sine over the cosine component, which you can see over here. And if you plug it in, your tau max is just going to be the square root. So if you look at the tau max and sigma max, you see the difference between tau max and sigma max is what? The average sigma. This is the only difference between them, because this rest of it here, this portion, is exactly that tau max. So sigma max and min are the average plus and minus tau max, as you can see over here. Okay? And also tau max could be written as you can see here, because as I said, one of them is, they are both basically plus and minus. This is average. So if you look at the sigma 1 and 2, if you have them, you can find tau max by taking the subtraction of the 2 and divide it by 2. I'll show you this better in the Mohr circle, this scenario. And another thing, if you look at tangent of 2 theta s and 2 theta p, you see they are the same as each other except for a negative and a reciprocal, right? Look at this here. If you look at this one and this one, you see they are the same, reciprocal and negative. So you can say that tangent of 2 theta p times tangent of 2 theta s, the multiplication is going to be -1. And you know, when tangent of two angles, whatever they are, multiplication of them is -1, that means those angles, some of them should be 90 degrees or about, or the lines that they represent should be at 90 degrees with respect to each other. So now if you divide both sides of this by 2, you can see that theta p plus theta s is 45 degrees or minus 45 degrees. And this is this one here. So if you have theta p plus minus 45 degrees, that is theta s. Okay, just keep that in mind as well. Okay, now with all these fancy formulas, let's go ahead and solve one problem here. So here we have a wide flange beam. It has a concentrated load somewhere here mid-span. And at point C, at location C, we know the state, we call it the state of stress. We know sigma x, we know sigma y, and we know tau xy at that location because of this distribution of stress, and it's shown here on this element. We want to find the principal stress at that location and show them on a proper sketch, and also find the maximum shear stress and again show them on proper sketch. Okay? So clearly, based on the formulas we learn, sigma 1 and 2 is equal to sigma average plus minus square root of the tau xy component squared plus the difference between the two divided by 2 squared, right? Here I just calculated them in MATLAB, and the maximum is 13,545 and the minimum is negative 5,444.9. Then we go for tangent of 2 times the angle. We need to have the angle if we want to draw the plot for the plane of maximum stress. We need to know the angle. So we go for tangent of 2 theta p, and we calculate it. It gives us two angles, which are 90 degrees apart, negative 1484 and 75.16 degrees. Now that we have these values, before I draw it, I need to know which one of these angles correspond to which one of these values. So I need to plug one of these angles into the formula for sigma x1 and see which one it will give me. So I go ahead and plug the first angle into the formula for sigma 1 and calculate the number. So here is what I did. Just make sure, since these angles are in degrees, use sine d and cosine d. This is tau xy. This is basically half of the average. This is the difference between sigma x and y divided by 2, and that is the average. And you see that the first angle corresponds to 13,000. Okay. So that is going to make life easy on us. So this corresponds to this, and this angle corresponds to that. So now if I want to show you the angle, it says it should go negative 14 degrees. And remember, positive rotation is counterclockwise. Okay, so we clearly have to go clockwise for 14 degrees. So we have to rotate it a little bit like this, where the angle between this normal and the x-axis, this angle is 1484 degrees. This is your theta p1. And then on this one, you can show a sigma of 1354.5. And then on the next angle, which is this one at 75 degrees, the stress is negative 54. So you have to reverse the direction. It's a compressive stress. So it is going to be 54,449. Okay, and then the question is, one big question that comes is, how much is the shear stress on these planes? So we found the normal stress on these planes, theta p1, and this one here, the angle of normal, this one is theta p2. But the question is, um, how much is the shear stress? And you can easily verify that if you plug in into the shear stress formula, theta p, if you plug in theta p in any of these, tau x1 y1 is going to be 0. We learned that on planes with principal normal stress, the shear is going to be 0, and let me show that to you. So all we need is to make sine 2 theta this coefficient with negative, cosine theta that positive, and there is no average. So I come back to here, there is no average. This one is going to be with the negative sign, right? Remember, and sine 2 theta. So we take this guy, or change this to sine 2 theta. And then plus tau xy, and this is going to be cosine 2 theta. And if you look at the number, it's 1.65. Now, is that number 0? No, because we rounded this angle. This angle was not perfectly 1485. It was a little bit off. We just rounded it. If you use the accurate angle exactly, this number should be 0. And look at the scale of the stress that you have. The stresses are in thousands of psi, right? 12,000, 4,000, 4,000. So when you get something like 1 psi, that is basically numerical error. So here is the original angle. You see that's 2 theta p. If I divide it by 2, the actual angle should be 835. So let me just go back and replace it with 835, see how much we get. You see, that's now practically 0. Okay, so on these planes, there is no shear stress, and therefore this is the plot for principal stress planes. That's for part A. Now for part B, you want to find the maximum shear stress and show them on a sketch properly oriented plane. Now in this case, do I need to go through all of these formulas and calculate them? The answer is no, not really. If you want to get tau max plus and minus, all you need to do is to basically subtract these two and divide it by 2. So I can say tau max in this case is simply going to be sigma 1 minus sigma 2 divided by 2. I can get that. And one plane has max plus of that, one plane has minus of that. And then the angle of theta s is theta p plus minus 45 degrees. Okay, so if I go with this angle, that is negative 1485 plus 45 and minus 45, you get negative 59.84, correct? That is minus 45, as I said. And the plus 1, so you have to subtract from that. So you are going to get around 30, negative or positive 30, and then 0.16 degrees. So these are the angles of the maximum and minimum shear stress, and the tau max, again, all you need is to subtract these two numbers and basically divide it by 2. So 13,545, correct? And so here 13,545, and then the other one is minus, so it's going to be minus minus or plus. And the other one is 54,449 divided by 2, and this is the number, okay, 9495 psi. This is sigma tau max, and if you want tau min, it's exactly negative of tau max. So it's going to be negative 9495 psi. There we go. So I found the max and the min shear stress and the angles for them. The question is which angle corresponds to which. Again, if you want, you can go ahead and plug one of those angles into basically this formula here, into this one. So theta P should go in this one, okay? I don't know if I made a mistake. This is theta S. Theta S should go into this one. So I plug in theta S in this one. Now, as I said, if you plug theta P in this one, you're going to get 0. But here, if I plug in theta S, right, let's go ahead and do it and see how much we come up with. So here I plugged in that negative 59, the first angle, and you see the number is that positive number. Okay, so again, clearly this corresponds to this one. And so this should correspond to this one. Good. Now the question is, what is the normal stress on the planes that have shear stress? So first let's plot this. So this time the planes that have maximum shear stress are at these angles, negative 59 and basically positive 30 degrees. So here I have to rotate it even more like this. And this plane that has this angle of 59 degrees, theta S1, that has a tau of positive on it. So it is going to be like this. Use a different color, like this one. And this is positive, so it's going to be upward. And the value is 94.95. And on the plane that is 30 degrees, which is this one, the stress is negative, so it is going to go downward like that, and the value is still going to be the same, 94.95. Now, on these planes for theta S1 and theta S2, where you have these shears, what are the normal stresses? Is there any normal stress on these planes? Remember, on theta P planes, the shear was 0. How about here? So if I go ahead and plug in theta S into this top one, what do I get? And you'll see that if you plug in, you'll get the average. So on both of these planes, the sigma is going to be the average sigma. And the average sigma is clearly, that's 40/50. So take these two, add them together, subtract, you get 40/50, and it's positive. So on both of these planes, there is a positive 40/50 normal stress. Sorry. There we go. Okay, so these are what? This is for maximum shear stress. These are for maximum normal stress. These are those planes, and we plotted them properly. There we go. So now, instead of doing all of this way, we can do it in a graphical way using the method developed by the German engineer Mohr. So it's called the Mohr circle, which is really interesting. So all you need is to form a circle, and I show you how to do it and then how to apply it to this previous problem, because it's really much easier to understand. So the way that the Mohr says you create your plane is this, your circle, and show the transformation is. It says the center of the circle is the average sigma. So the average sigma is the center of this the circle. Now, what are the axes? Before we go to the circle, we have to know what are the axes. So the horizontal axis is the sigma axis, positive to the right, and the vertical axis is shear but positive down. So that's the first thing you do. You plot this kind of, as you can see, this kind of axis. Then what you do is you go and determine the average sigma. So that is where the average sigma is. That is the center of the circle. Then you need to determine 2 points. What are these 2 points? One is for plane A, the vertical plane that you have sigma x and tau xy on it, and the other one is for plane B, which has sigma y and negative tau xy on it. So go ahead and plot, find those points on this coordinate system and show it. So if you do so, you see that sigma x and tau xy is going to come here. This value is sigma x, and this value here, if you projected this value here, right, look, that is tau xy. So you get plane A. For plane B, this is sigma y, this distance, and this distance here is negative tau xy because it's clockwise. So counterclockwise taus are positive, clockwise taus are what? Negative. Okay, so this kind of tau, is negative. This kind of tau is positive. Or I write it like this. So point B is there, point A is there. Once you have point A and point B, so this is A, this is B, that's all you need to have. Now you have 3 points on the circle, the center, and 2 points on it. Guess what? You can fit a circle to it. And let me grab the circle tool. Let's see if I can plot a circle. So you need a circle that basically passes through these points and have that point as its center, something like this. Okay, let me move this a little bit off here. That might be more interesting. There we go. So you got the Mohr circle. It's done. Now, what's so special about it? Guess what? Now, if you want your maximum sigma, this is the maximum sigma. That is sigma 1. If you want your minimum sigma, this point is your minimum sigma. If you want tau max and tau min, this point here is tau max. And the negative of that up here, this is tau min, which is negative tau max. You see? And then, if you want the angle of the major plane, look here. This is A, this here is sigma 1 and angle theta p, of course, correct? So if the line connecting the center to A, this is corresponding to 0 angle. This is theta p, but remember on the circle, if you look at the formulas, everything in these formulas is based on 2 times angle. So the angles on this circle are measured by 2 times what they are. So this is going to be 2 times theta p. And since this angle is counterclockwise, so theta p1 is going to be positive. Now for theta p2, it's the angle from A to sigma 2, so it is going to be this angle. That is 2 times theta p number 2, that is 2p theta p number 1, and you see both of them are positive because both are counterclockwise. Now what about theta s1 and theta s2? Well, this plane here is where tau max is, and this is theta s, and if you measure it from A, which is 0 angle, this angle here is 2 times theta s1 and is clockwise, so it's negative. And this plane here is where theta s is number 2, the minimum, and that is this angle here, and basically that is a positive angle. Okay, so from here you can find all of those values, and if you want it at any other angle, you can also do that. So for instance, they say at a plane for theta equal something, 75 degrees, what is sigma x1, what is tau x1 y1, and what is sigma y, not sigma y1, just those two, right? So say at this plane, how much are those? So instead of going through these formulas, these two, you can come back at the circle, and all you need is to multiply that angle by 2 and then move from A. So 2 times that is 150. So let's say 150 brings you to a location like this. So this angle, let's say, how do I show it? This angle here, that angle is 150. Then if you can calculate this point here, that is your tau x1, y1. And this point here, if you project it, this here is your sigma x1. And all you need to do is through simple trigonometry. Okay? And why this circle is valid the way it is, because it's not really hard to show that. Look here. If I subtract the average from sigma x1, so if you wondered how he come up with this beautiful thing, if I take this average and subtract it from sigma x1, you get sigma x1 minus sigma average is equal to, let's call this guy A, if you don't mind, and call this B. And this theta, just 2 theta, just call it theta. It doesn't matter. So it's going to be A cosine of 2 theta, and then plus B times sine 2 theta. And then tau x1, y1, if you look at it, it is, look, it's negative A sine 2 theta. And then plus B cosine 2 theta. Correct? Now, this is my x-axis, this is my y-axis in that Mohr circle. So all I need is to square them. And if I do that and then add them together, you'll see that sigma x1 minus sigma average squared plus tau x1 y1 squared is going to be these guys squared. Now, when you square them and add them together, you're going to get A cosine squared of 2 theta plus A squared sine squared 2 theta. So you simply get A squared. These two, when you add them, square them and add them, you get B squared. And then the product terms, this is positive 2ab sine 2 theta cosine theta. This is negative 2ab sine 2 theta cosine 2 theta. They cancel each other. So you simply get this. Now, if this is the radius of my circle, this is clearly the equation of a circle, where the center of it is at 0.0 for tau and sigma average for the x-axis, and the radius of it is r. And r is how much? R is this square root here, basically, this guy. That is r. And if you look at this circle, that's exactly what it is. The center of it is at point sigma average and 0. And the radius of it, this radius, if you calculate it for any point, that is exactly that, the square root, which is tau max. Remember, tau max was the square root, correct? Look back. Tau max is what? Is the radius. And if you look here, this radius here is exactly equal to the tau max. And negative of that is negative tau max. And if you add that, the square root, to the sigma average, that's sigma max, sigma 1. And if you subtract it from sigma average, that's sigma min. And those are these two formulas here. Look at them. The average plus minus the radius, that's sigma 1 and sigma 2. So you clearly see where the Mohr circle is coming from. Okay, now to practice that, we're going to do it on the same example that we did and see if we can come up with the same answers that we had. So here we're going to go and draw the circle again and the coordinate frame. So in this case, your sigma y is negative, so we better move this guy a little bit this way. Remember, this is your sigma, this is your tau. The first thing you need to find is the center. So you need to find the sigma average, which in this case is sigma x plus y divided by 2. And we add these and subtract. You're going to get 40, 50. So that point and 0 tau, that is where the center of the circle is. Then we want plane A. Plane A, remember, has sigma and tau. Okay, and in this case, your tau is negative. So sigma x of 12,300 somewhere here, but your tau is negative. Okay, so you're going to go up there. So this point here is 4,200 or negative 4,200, and this point here is 1230, 12,300. So that point there is plane A, this plane. And for plane B, you have sigma y, which is negative again. So it is going to go this way, 4,200. And it's always negative of that, so it's going to go like this, and that is 4,700. So it is clearly positive this time. So that is negative 4,200 over there, as you can see. And then I made a mistake on this one. This is 47. This guy was 4,700. This one here, not 4,200. And negative of that for or positive of that, because this is the positive axis, for positive 4,700, this is going to be for B. So B is going to be right there. So now these 3 points, although they don't look, they are so nicely spread, and the reason for that is this 12,000. That should be way further down the axis. Okay, so ideally these points should form a circle together. So what I need to do is probably, you have to do this really on a scale, otherwise you are going to end up with numbers that are really off. So here, that's sigma, and for that 12,000, probably I need to end up somewhere right there. Okay, and so this is going to be point A. There we go. So now I have these 3 points, and now I can fit a big circle to them. So go and grab a circle, and this should be a large circle to fit all of these guys. Now, of course, this is an ellipse, but if you can fit a big circle to them, then it should be good to go. Okay, so let's say a circle like this, and now if I want to find my maximum and minimum values and everything, so this point is my sigma 1, this point is my sigma 2, correct? And then I can get my tau max and tau min, so this is my tau max, and I can find any other thing that is needed. So clearly, if I want sigma max, the first thing I need to do is to find the radius. And for radius, I need to find this distance from here to here. I need this radius, and it's not really hard to do because you know the coordinates of these points, correct? So if you know the coordinates of these points, you just can subtract and find it. So this radius is clearly going to be the square root of, this point has 1230 and negative 47. This point is 450. So all you need to do is to subtract that 12,300, correct, minus this point 4050, and square it, and then add it to the y component, which is 4700, and square it. And that should give you your tau max also, because that radius, as I said, this radius here is the same as tau max. So that will directly give me tau max, and I bet if you use your calculator, you are going to get the same number as we found before. Your tau max should be, let's see if you have it here, so 94.95. So you are going to get 94 and 95 psi. Okay, that's all you need to do. So now it goes all to geometry as opposed to using the tricks formula. And here is the proof of it in MATLAB, so you don't think I'm just making it up. So here is that radius 94.949, rounded 94.95. So that is your tau max. And now all I need for sigma 1 is to say sigma 1 is literally sigma average, correct? Because remember, this distance is also r. So all I need is to add that to 4050, the average sigma. Just need to add that 94.95 to it, and that should give me that 13,000 number that we found. You can see it is going to be 13,000, and that is going to be 545 psi, and that is the same number as before. And then if you want sigma 2 here, again, remember that this distance is also r. So clearly sigma 2 is going to be equal to that 4050 minus that 9,000. Correct? And so all I need is 94.95 here. And I should be getting my negative 5,000 number. So it should be 5445 psi, and that is the same as my sigma 2, as you can see over here. So that is this number, and the other one is this number. Okay, so you see that we got all of this, and you know tau min is clearly negative tau max, right? Because again, this is r as well, this line. Use a different color, so this one is also r, so it's just going to be negative 9,000. That is going to be your tau min. Now if I want my angle, this is sigma 1 plane, this is A plane. This is the angle going from A to sigma 1, that is 2 times theta p number 1. Clearly you see this angle is negative. So how much is it? Well, I can find it through a triangle, and that is this triangle going from this point, let's call this point C, going from C to A, and then dropping it down to this point here, whatever you want to call this point, let's call it D. So if you look at the triangle CAD, tangent of 2 theta PA, that is equal to what? Is equal to basically the vertical side. How much is the vertical side? That is 4,700 divided by what? Divided by the horizontal side, which is the distance from this point D to the average. So it is basically 12,300 and then minus 4050. And again, if you use your calculator and find this angle, clearly you're going to see that it is going to be that same 14 degrees that we found, right? This one. But since it's clockwise, clearly the angle is going to be negative, right? So let's just do this one with calculator as well for you. So here is that angle, and that's 2 times theta p, so divided by 2, you see, 1483.5 or 1484, and again, it's going to be negative. So you see that everything is exactly going as planned. So theta p, again, p1 is going to be negative of 1484. And if you look at the other angle, theta p2, clearly that's the angle from A to sigma 2 plane. So that is this angle here. And clearly it's going to be, the next angle is going to be 90 plus theta 1, and you see it's positive. If you want the angle to theta s1, that is the angle from A to the plane of tau max. So that is this angle. So that angle is 2 times theta s1. 1. This one, remember, it was 2 times theta P2. And if you want the angle from A to minimum shear stress, that's this angle. That is 2 times theta S2. And the good thing is here, I don't need to plug the angles into the formula, see which one corresponds to which. I can just visually see that. And that is really, really beautiful. Okay, so this Mohr circle is a really good representation of the state of the stress and stress transformation. One last thing before we finish this video is, in cases that we need to look at 3D stress, the Mohr circle, and the stress distribution is still plane stress, but we need to find the stresses, the max and the min in 3D. There are going to be 3 Mohr circles. So you have this one, and you have this one, and you have sigma x, sigma y, tau xy, and the third stress, sigma z, is going to be 0 in that case, okay, because it's a plane stress, but sigma x and y are given to you, as well as tau xy, they are not 0, and they say what is the maximum stress in 3D as opposed to 2D. In that case, remember, there are going to be 3 circles. So let's say your center of the tau x and tau y is here, and point A is here, and point B is here. Okay, so in that case, you are, of course, going to get your Mohr circle that I just made for you, right? So you're going to get something like this, for instance, something like that. Let's see. Okay, this is the one formed by sigma x and sigma y, but remember, there is one that is between sigma y and 0, so there is one point here also that is corresponding to sigma z of 0, so you're going to get another circle. So this yellow one is the last one that is the biggest, and now clearly if you want your tau max, you have to find the center of the big circle, this yellow one, and then this radius here is going to be your tau max, not the one for the blue. Okay, so in 3D, there are 3 circles, even if the case is still plane stress and there is sigma z of 0. So pay attention that if they ask you for that, this needs a separate video of its own, but just one, I wanted to give you a heads up that if you see 3 Mohr circles, don't be surprised they are finding the maximum stress in 3D, even though the case is a stress plane, plane stress. So thank you so much for your attention. I'll see you in the next lecture.